Please hit subscribe.
This problem appears at the qualifying examinations for applicants for Japanese government or MEXT scholarships 2020. There are two mathematics exams, one for social sciences, Mathematics A, and another for natural sciences, Mathematics B. This problem is from the 2020 Mathematics B questionnaire. The answer key and original questions are linked in the description. This is part 2 of problem 3. And we are asked to find the area S of the figure A, which is bounded by C and the x-axis. So the figure A is defined as the figure bounded by C, which is this curve, and bounded by the x-axis. Let us list down a few items that might help us solve the problem. First is that the area S bounded by C and the x-axis is actually the sum of the areas of the individual parts. So that's what this first part means. So this means that the area S, the total area S, is actually the sum of this area here. For example, this curve here is the curve C. So the area S is the sum of the area here, the area here, and the area here. That's what this means. And you see S sub I is actually the area, that's the integral of y with respect to x. So that's the area from x sub 1 to x sub 1 plus, rather x sub I to x sub I plus 1. So for example, for this area here, that's from x sub I to x sub I plus 1. So this is that S sub I here. And we see that we put absolute value symbols here because we want the positive area. So the area here should be positive, here should be positive, here should be positive. And we need that absolute value symbol because we know that if the curve falls below the x-axis, then the area there is negative. So if you just compute the integral of this region here from x of theta I to x of theta I plus 1, then you're going to get a negative value. And we do not want to add that to the area. We want the positive areas to add up. So if it's negative, we need to get the absolute value. And that's what this means here. We need to find the absolute values of the area. So it's important that we know where the y becomes negative. If the y's are all positive, then we don't have a problem because it's just one whole big area. But if there are regions where the y's are negative, then we need to find those. And lastly, okay, so this is just an illustration where the area is positive. This is when y is positive and the areas here are also positive. But down here we have y's that are negative, and so the area here, S sub I, are also negative. And lastly, we have Wallis formula. So this is a convenient formula. You don't really need this for this problem, but this is going to help our integration. It's going to make it quick. So Wallis formula says that the integral from 0 to pi over 2 of sine raised to the nth power d theta is equal to the integral of cosine raised to the nth power. So the important part here is the important parts here are the limits of integration. It should be from 0 to pi over 2. Here it should be 0 to pi over 2. And then the exponents should be the same, n. Now, if you have this can be easily evaluated using the following formula. So if n is even, then all you need to do is attach a pi over 2 here at the end, and then you start by putting n in the denominator, then subtract 1, put it in the numerator, subtract another 1, put it in the denominator, subtract another 1, put it in the numerator, and do this all the way to 1/2. And this product is the definite integral that we're looking for. Now, if n is odd, then we chuck in 1 here, and then the same thing, we just start with n in the denominator, subtract 1, put it in the numerator, subtract 1, put it in the denominator, subtract 1, put it in the numerator, do it again and again until you reach 2/3 here. You see, after 2, you subtract 1, then it will be 1 in the denominator here. So it's pretty easy to remember this way. So this is going to make the integration a little bit easier for us. So let's just copy the key ideas that we had in the previous slide, put it here. And now we recall from this second idea here that if we have a curve that if we have a part of the curve that is below the x-axis, then this area here will be negative. And we do not want to add a negative area. We want to get the absolute value of this. And so the first step in our process is to actually find the locations of the on the curve where the y's are negative. So we want to find, if any, these regions in here. So let's find that. We will do that first, and then if there are y's that are below the x-axis, we will have to compute the areas separately. So we need to compute the area here, and then we need to compute the area here, and then we need to compute the area here, and we do them separately because again, this will be negative, here will be positive and positive, but we have to turn them all into positive, so we'll get the absolute values of all these. So let's do this. Let's first do looking for the values where y is or y are negative. We start with the value for y, which is y of theta equals 1 minus cosine theta, and the problem states that the theta will be between 0 and 2 pi. If that is the case, then we start with trigonometry to see if this value of y, if any of these values actually go below 0. So that's what we're going to try to find out. So we start with trigonometry. We know from trigonometry that the value of cosine theta for any theta actually falls between -1 and 1. Now, our goal is to arrive at this expression here from this starting point. So we want to get 1 minus cosine theta and see if that is ever less than 0. So we chucked in a negative sign here, and we do that by multiplying -1 to all sides of this inequality. And when we do that, we obtain this. So the inequality symbols flip, and then we get a negative sign here. We lose the negative sign here, we get a negative sign here. And then we just add 1 on all sides. And now this is what we get. We get 1 plus 1, 1 minus cosine theta, 1 minus 1. So now we have this bit here, and we can replace it with y of theta. So we get 2 is greater than or equal to y of theta is greater than or equal to 0. What this tells us is that y of theta never falls below 0. So it's always positive, and in fact, it's always less than or equal to 2. And because we know this, now we do not even have to break the integral. So we do not have to worry about this because we now know that our y's are all positive. Everything falls above the x-axis. And so we just need to find the limits here now. So the limits here would be from where theta is 0, because that's the limit here, 0 to 2 pi. So that's what we'll do. And again, we've just said that we don't have to worry about this anymore, so we do not have to compute the area separately because the y's here are all greater than or equal to 0. And so our integral is from x0 to x sub n. Again, x sub 0 is just when theta equals 0, and x sub n is just when theta is 2 pi. And we'll do that in the next slide. So here we first thing we do is we replace this with theta. So to find the area, we need y dx. So y times dx. But we are given y and x in terms of theta. So we express this in terms of theta. And the way we do that is quite simple. We just chuck in a d theta under dx here, and now we can integrate with respect to theta. So this is the derivative of dx with respect to theta. And then our limits of integration changes from x, because we had x here originally. Now we replace it with theta, because now we are integrating with respect to theta. And so we just replace it with the values of these. So y of theta is 1 minus cosine theta, and dx d theta is 1 minus cosine of theta. We know this from part 1 of this problem. And this is from 0 to 2 pi. And we just do the multiplication and we get the following: 1 minus 2 cosine theta plus sine squared of theta, or rather cosine squared of theta. And then we separate the terms. So we get this. We have an integral of d theta, just one, then the integral of this cosine theta here, then the integral of this cosine squared theta. And this bit here is easy because this is just theta from 0 to 2 pi. This one is also easy. We know immediately that this is 0 because we are integrating from 0 to 2 pi. So when we are integrating a sine function or a cosine function from 0 to its period, in this case the period is 2 pi, then what we will get is 0, because if we recall, for example, in this case we have a cosine function. The cosine function looks like this. So here would be 2 pi, and here would be 0. And if we're integrating from 0 to 2 pi, that means we're getting the area from 0 to 2 pi. This bit here is equal to this bit, and this bit is also, because of the symmetry of the cosine function, this area here is equal to the area here plus the area here. But because here we have a negative area, when we add them all together, we get 0. So this is also true for the sine function. And so we know that this bit here goes to 0. And now this bit, we can use Wallis formula. So this one just becomes 2 pi, because that's just theta from 0 to 2 pi. So 2 pi minus 0. This one is 0. And now here, for Wallis formula, we need to make sure that we are integrating from 0 to pi over 2. And again, this is the square of cosine. And so if you square cosine, so if you have it, a cosine function like this, if you square this, that's just going to go a little bit like that. If you square this bit here, it's just going to go above the x-axis. But then the shape of that is just the mirror image of the first bit here. Again, that's because of the symmetry of the cosine function. And the same is true with this bit. It's just going to go to a positive x-axis. And again, the shape is the shape of this is the mirror of this shape, which is again the mirror of this shape, which is the mirror of the shape of this when it's squared. So it looks like we have four bits here that are of the same area, and each of them is actually from 0 to pi over 2. And so we can break 0 to 2 pi into 4 bits of the same area, and that area is the same as the area under the curve of cosine squared from 0 to pi over 2 in here. Now this is a good form because now we can use Wallis formula. So let's just do that. So again, we retain the 2 pi here, we retain the 4 here, and from Wallis formula, this is even. So we use pi over 2 at the end. We chuck in pi over 2, and then we put this in the denominator, So we put 2 here in the denominator, so that's 2. Then we subtract 1. So 2 minus 1 is just 1. And that's the last term here. And so our process ends here. Now we just simplify that 2 pi plus, so the 4 and the 2 here cancel. So 2 pi plus pi. And so we're looking for the area that is 3 pi. If you learned something new today, please help my channel by clicking the subscribe button and the bell for the notifications. See ya!